just to kind of reiterate the situation, you got your slice of Earth, okay? Miss McGrain cut this for us over the Thanksgiving holiday, and she knew that it had to be a little bit more than a meter long in order to fit the model, right? Okay. If I wanted to start over and I wanted to go center of Earth to center of Moon, which is 384,000 kilometers from Earth, center to center, how long of a piece of paper do I need to have? You have an answer?
3,847 meters.
Say that again.
3,847 meters.
3,840 centimeters?
Yes.
And where did you come up with that number?
I did the conversion factor. I divided it by 100.
Okay.
Moved the decimal over twice.
So let's just write that out so that we all are on the same page. So 384,000 kilometers. Is that kind of where you started?
Mm-hmm.
And then you set up your little chart just like you had on the yellow paper, right? And again, if you know how to do this, if this makes sense, then you don't need to necessarily write it out. But sometimes it's a good reminder that we said that 1 centimeter was equal to, was it 100 kilometers? Is that right?
Yes.
Okay. So we're going to say 1 centimeter on top, 100 kilometers on the bottom. Why do we put the 100 kilometers on the bottom? Yeah, we want to cancel out those units, right? So we want to get the kilometers on top and the kilometers on the bottom to go away. And so then we can say, oh, we're just going to divide by 100, which is what Colin said a minute ago. So that's going to be 3,840, because we're going to get rid of 2 of those zeros, and that's going to be the number of centimeters. Now, how many, this is the question that I really want to know too. So if you were my student helper and I said, okay, we're going to do this, I need you to get me some paper that's 3,840 centimeters long. Okay, like, do I just need to get a bunch of meter sticks? How many meters is that? That's what I was about to ask you. How many meters are in a centimeter? Centa means, what does century mean? Do you know?
100.
Century is 100 years, right? Centa is 100. There are 100 centimeters in 1 meter. There are 100 centimeters in a meter. So that means, so we need to move the decimal over how many times? 2.
38.4.
So that means that my piece of paper needs to be 38.4 meters long. I mean, if I'm actually going to send you down to the paper, to the roll, then yes, you can round up. But I just want to make sure you really get this. So if I gave this to Michaela and had her stand over here, okay, and this represents the core of the Earth. Are you with me here? Okay, and then this represents the Earth. This is the crust. This is where you're standing. Here are all of the layers of the atmosphere, and it goes out to here. I would need all of you and almost all of my second period class to hold meter sticks, one after the other, after the other, after the other. 38 people. Okay, that's beyond the distance of this building. Are you with me there? That's how far out the moon would be. That's pretty far.
That's pretty.
Right? I just want you to have like it's hard to picture how far away, like the moon seems, oh yeah, it's super close. It's pretty far away. And the sun's even further than that, right? So it's just, just kind of a heads up thing. All right. Questions on the conversion? Are we okay? Sweet. All right. Would you pull out your Earth layers notes? This thing that looked like the pie. Do you remember this from yesterday? We were nearly done with this. Does anybody, you guys don't have this, right? Was there any of my friends here that were not here yesterday? No, I don't. I got mine up here. But thank you very much, Haley. I appreciate your offer. Sometimes I do. Sometimes I actually am like, yes. So, scientists, I'd love your attention for just a moment, please. Not just a moment, a long time, actually. I just want to remind you of these layers, right? All of these different parts. It's kind of like a big gobstopper with all of these different layers. And all of the layers have different things going on in them, okay? The layer that we can see and know and study the most easily is the crust, right? The thing that we're standing on. All of this other stuff we have been trying to understand for a long time. And in fact, do geologists really understand this stuff down here?
Not really.
Not really. That means that there are still jobs, and there will be jobs for many years studying what's going on in the center of the earth, in the core, and in the mantle. There's a lot of funny stuff going on in there. Yesterday, we started watching a video, and we got, I would think about halfway through it. It's just like a 3-minute video. So I'm just going to play that for you again to get your brain back in there. We're going to take a couple more notes, and then we will move on from that. So I'm just going to throw this video back on. We're going to skip the video in 3 seconds. Skip ad. There we go. All right.
We were at 2 minutes.
Okay. Well,
That's all right.
we'll take the 2 minutes to get our brains back in there.
Hey everyone, Jacqueline Howard here. Ever wonder what it's like inside our planet? Come with me on a subterranean tour all the way from the rocky crust where we live to the layer known as the mantle to the wild, half-solid, half-liquid core of the earth. We'll also be stopping by a newly discovered underground ocean. Let's go. First stop, Earth's crust, the outermost layer where we live. The crust is made up of several elements, from iron to magnesium to sulfur, and its thickness ranges. The continental crust, the stuff found under land, can be up to around 50 miles thick, while the oceanic crust, the stuff found under our oceans, is around 4 miles thick. But let's see what lies below that. Now we're about 50 miles below the surface, at the uppermost region of the mantle. This layer is made up of rock that's rich in oxygen, iron, magnesium, aluminum, and it extends from here all the way down to around 1,800 miles below the surface.
That's a long way.
The mantle is also where molten rock known as magma can form, the stuff that flows upward during volcanic eruptions, at which point the magma becomes lava. This was pretty much the picture scientists had of the mantle until earlier this year, when a vast, hidden ocean of water was discovered some 400 miles beneath North America. It goes to show that the rocks down here have a pretty impressive capacity to store water. But now let's drill a little deeper. You ready? Here we are, 1,800 miles down at the Earth's outer core, which runs all the way down to around 3,000 miles. This is a layer of molten iron that surrounds Earth's inner core, and it's really, really hot down here. In fact, it's between 7,200 and 9,000 degrees Fahrenheit. But if you think that's torching, wait until we reach the center of the Earth. And we made it to around 3,000 miles down, the uppermost part of the Earth's inner core. Like the outer core, it's made of mostly iron, but the pressure down here is so intense, the stuff is solid. It's almost incomprehensibly hot. It's about 11,000 degrees Fahrenheit down here. That's hotter than the surface of the sun. Now, the actual center of the Earth is about 4,000 miles down, but I'm starting to sweat, so let's skip that and head back up to the surface. Phew, back on the surface. If my virtual tour of the Earth's interior had been a real one, it would have been a first. We all know that no one's ventured beyond Earth's crust. But then, how do we know what's down there beyond the crust? Scientists use waves of energy called seismic waves emitted by earthquakes to measure what type of material is inside Earth and where that material lies. You see, as seismic waves travel through our planet, the rate in which they're traveling, whether they're moving fast or slow, reveals what exactly they're traveling through, whether that material is solid, liquid, or something else. Now you know. Leave your thoughts on what's lurking inside Earth in the comments, and come on, talk nerdy to me.
Okay. That was kind of silly. All right. Is that making sense? Nothing too wild and crazy there? Okay. On your notes sheet, there's one little section that we have not yet done, right? What does it say? Why? Yeah, I think so. I just have the picture, so I don't have the actual sheet printed off. That's why I asked you. I think it was why does the Earth have layers? So we need to answer that question. Why does it? Any idea? It's a weird question. Any ideas? Any like hints or inklings of things? It doesn't have to be right. You're just like, come on, Miss Carbling, tell me. I can't wait to find out. Is that what you're saying to yourself? Yeah, I know it is. All right, let me tell you. We talked about it yesterday. This is the answer right there. Density. Density has to do with the reason the Earth has layers. We will talk more about density and actually, get into exactly how and why it works. But I want to give you two quick examples. Okay? Pour some water in a glass, then you put an ice cube in it. What's the ice cube going to do? It's going to float, right? Why does the ice cube float? Do you know? Because it's, what'd you say?
Less dense in the water.
Less dense than the water. That's what he says. Do you agree with that? Yeah. Yeah, it's less dense than the water. What does that mean? It means that the molecules are packed not as tight, right, within ice as compared to the liquid water. Okay? Yeah. Another one for you. You have a balloon not filled with like regular air, but a balloon filled with helium, our favorite, right? The one that comes from the sun. Yeah. When you hold that balloon filled with helium, where does it go? Up, right? If you happen to accidentally let go of the string, oh no! Up it goes. Why? And then you start crying?
No, my brother.
Oh.
Oh. I'll be crying too.
It's a sad thing. Like you get attached to these, spheres of helium. Why does that happen? Maybe you can wipe away his tears and say, well, let me tell you what just happened. That's really what I would do. Let me tell you what just happened. Why does it do that? Why does the balloon go up instead of just sitting right there? Go, Siniya. That's exactly right. Helium gas is less dense than the air that we breathe. Less dense means that it goes where? Up. You can fill balloons, you can fill, whatever vessels with other kinds of gas, and some of them are more dense than air. If I fill it up with something more dense than air, I think that nitrogen is more dense than air. Where's that balloon going to go? Down. It's like the opposite. That one, you could get your brother a balloon filled with nitrogen and it would fall down. That he would never lose his secret. I think it is. I'm not gonna, but I'm pretty sure that that's true. Yeah. Helium makes it. Yeah. I think it is. I'm not an expert on it though, so don't quote me on that. We can look it up. Okay. So the answer, the thing that I want you to write down, please don't write on my desk, friends. That would be vandalism right there. Yeah. So let's respect the property. Thank you. Why does the Earth have layers? Because the different layers are made of different stuff, aren't they? Yeah. And so the more dense, we wrote this yesterday too. The more dense it is, the further down it's going to fall. Okay? The more dense it is, the further down it will go. The most dense stuff is in the middle. Then less and less and less and less and less. Density is the key. Why does the Earth have layers? It's because the materials that make up layers have different densities. And remember, densities just means how tightly packed their atoms or their molecules or their stuff. You can just say stuff if that makes you happier. How tightly packed that stuff is. Okay? More dense, okay, means more tightly packed and it's going to be closer to the center of the Earth because it sinks down. Okay. That's it. Why does the Earth have layers? The different materials have different density. Boom, you're done. We'll do some density column stuff and some density calculations later. That's just the first kind of peek into it. I'm going to share one other video with you. Hey, it's called Why Does the Earth Have Layers? So maybe it'll have some more information for us as well. Let's take a look here. It's okay to be smart. You guys know that though, right?
Hey, I'm just making a planet.
Oh!
Well, this is how planets like
Oh,
Earth
I didn't
get
see
their
that.
structure
Right.
anyway, because of different layers of density. Even today, with all of our modern technology, we've only been able to drill about a third of the way through Earth's crust. So how do we really know if it's solid, liquid, hollow? Luckily, Earth has this tendency to violently shake and occasionally burp up some of its insides. And that's taught us a lot about our planet's guts without having to go down there. We're used to seeing density at work. That's the same reason that the atmosphere, the least dense part of our planet, is on the outside. And the crust, the second least dense part of the Earth, is beneath our feet. Because I'm less dense than the dirt, I don't sink into the ground. And even though there's about 1 ton of atmosphere above my head, it's not dense enough to send me floating. The main layers of the Earth are organized in the same way. Depending on whether they're divided up by how they squish around or what they're made of, geologists give different names to the different layers of the Earth. So that's how it is now. But to really understand why the Earth is organized the way it is, we need to go back to before our planet even existed. In the very young universe, hydrogen and helium were pretty much the only elements around. They condensed into stars, began the process of nuclear fusion, and eventually died, spitting heavier elements from carbon and oxygen to things like nickel and gold back out into the universe. One of those heavy elements, iron, is the most stable element produced outside of a supernova, and the early universe produced a lot of iron. That'll be important in a second. Fresh hydrogen and helium went on to form new stars like our sun, and the heavier elements collided to form the dust and debris that would become our solar system's planets and moons, asteroids, and everything else. High temperatures in the early inner solar system meant that light volatile elements could only condense further out, which is why the inner planets of our solar system are dense and rocky, while outer gas giants like Saturn could hypothetically float in a really big swimming pool. After proto-Earth grew larger, radioactivity, gravity, and violent boom booms melted that messy mixture of rocks and minerals, and this is where things started to get organized. Just like that tower of density, the heaviest materials like iron and nickel worked their way to the core. The lighter materials like aluminum and silicon stayed near the surface. The inner core experiences pressures more than 3 million times what we do on Earth's surface, which means that despite being as hot as the surface of the sun, the iron in our planet's inner sphere is likely solid and not liquid. The outer core is most likely liquid because it's hot, but not under as much pressure as the inner core. We know that's the case because of earthquakes up here on the surface. As certain kinds of seismic waves travel through the Earth, the liquid outer core either refracts them or blocks them altogether. And that creates seismic shadows on the opposite side of the planet. If you want to use pressure to melt metal at home, just stack up 16 million pennies. The one on the bottom should liquefy in that. Mercury is so close to the sun that its atmosphere has long since blown away. But luckily for you and me, our liquid metal outer core lets us have an atmosphere. Deep metallic convection currents create a magnetic field that shields Earth from the solar wind. Otherwise, we'd be pounded with deadly radiation, our atmosphere would be blown away, and Earth really wouldn't be a very lifey place. Over time, Earth continues to cool, so more and more of its liquid outer core is turning solid, and we're shrinking little by little. Every earthquake that we feel is Earth taking one step closer to cooling off. and becoming a real third rock from the sun. So there you have it. Like Carl Sagan said, we are star stuff who has taken its density into its own hands. It's density, right?
Density.
Stay curious. People have been looking at clouds since people have been people.
That's hilarious.
Flowing shapes might have been our first art
Oh,
or
stop.
the characters in our first stories. And we still love.
What's scary? What are you upset about? Why are you scared? What's that? The planet is getting smaller, but did you see the little thing at the bottom that said, yes, the Earth is getting smaller, but our solar system isn't going to last that long? Because what's going to happen before our solar system or our Earth gets too small? Yeah, our sun is going to eat us up because it's going to turn into a. Anybody?
A red giant.
Not a super giant. We're not that big.
Oh my.
Just say
A red giant.
red giant, right? Yeah. So the funny thing is that all of these things happen, but they all happen at this. Like we're telling lots of stories all at the same time. Okay. Questions that you have right now? The last part of what?
Yeah, but the answer, I said the Earth. That's where it ended.
I don't know. The Earth. Yeah, I can totally go back.
Thank you.
Because it sinks?
Because it's there. We go.
There you go. It's close to the center because the more dense stuff sinks down. I mean, that's essentially what it is, right? Yeah. It's weird. Density is like the key to everything when it comes to this business. All right. We're rocking. I love this. Okay. Let me peek here. Capture question 4.3b. Pull it out. Pull your capture questions out again.
Yeah.
What? I know it's weird, right? 2 capture questions in one day? That's great. It's like double the capture questions. It's 2 for Thursday? That's not a thing. Could be Friday, but I don't want it to be Tuesday. So we'll call it 2 for Thursday.
I'd like to be Friday.
Well, tomorrow. Lucky for you, it's coming. All right. Capture questions out again. 4.3b. Do you think any of the layers of the Earth move? What do you think?
What do you mean by
I want you to take it at face value, my dear. Answer the question as it's written, right? I'm not grading you on this. It's fodder for conversation. The beauty of learning, the beauty of having opportunity for academic discussion, right? The question says, do you think any of the layers of the Earth move? Can I help you find something?
Sorry, I can bring my.
No, it's okay. I don't know if I have them. Okay. I'm sorry. I'll look in a little bit. This is a big question. This is a deep question. Get it? Deep. I'm doing all kinds of bad puns today. You get it? That's good, right?
That's it.
I know. Why don't you talk to your teammates? Go, go, go. What do you think? Do they move? Everything sits still.
Yes, because the molecules.
All right. Are you ready? Somebody give me the 3 primary layers, or I guess 4 primary layers of the Earth real quick first. Go.
Crust, the mantle, and the core.
Oops, except I can't write. Yeah, let's do the 2 separate because things might be different. I did say 3, and then I corrected myself and said 4.
Inner core, and the outer core. She said 3. I was listening.
Shh, stop fighting, friends. It doesn't matter that much. All right, so let's talk about it one by one. But I'll let you pick. I will start with
Sorry. Actually,
Go, Sydney, yeah.
molten lava.
The molten, yeah, so I'm glad that you said that because I misspoke yesterday and I didn't correct the mistake that was made, and I apologize for that. You said the molten lava. So there's a distinction that I want to make sure that I help you make so that you can sound like a knowledgeable individual. Lava is only lava once it has come up from the surface. Just a little side note. You can write that down on your capture questions. Just a little side note so you don't forget. Lava is only lava only after it has reached the Earth's surface. Prior to reaching the Earth's surface, what is it? Magma. Below the surface, liquid rock is magma. So I wanted to clarify that. So now you all know, now there's no surprise. Now you all sound as intelligent as you are because you know that's the right phrase, the right terminology. All right. So tell me again, now that we know that, what magma are you talking about? The mantle? Yeah, so you're saying that the magma in the mantle moves? Is that what you said? You said something more clever than that, though. What did you say before? Can anybody help me out? What did she say? It's, yeah. So magma in the mantle will say flows due to convection currents. Is that okay? Love it. All right. So the answer that Sydney is giving us is yes, I think that at least one of the layers moves, that being the mantle. The magma in the mantle flows due to convection currents. All right. Pick another layer and you can say yes or no and tell me a reason that you may or may not think so. Yeah.
This isn't really a layer, but don't we have earthquakes because like places are shifting?
And that is totally a layer. Which layer is that involved with? Well, they're the plates of the crust. So that's exactly right. Yes, yes. So does the crust move? Yes, indeed it does. Yeah. Livy says earthquakes. I've heard of those. Can't remember. Have you seen or experienced an earthquake yourself? Not that you're aware of. Earthquakes are the movement of plates, right? And we haven't really defined those plates yet, but plates are part of the crust. So yeah, for sure. 2 down, 2 to go. We're halfway there. Outer core. Does it move? Do you think? Is there movement in the outer core? Beth says yes, kind of uncertainly though. She doesn't want to commit. Should we look and see what the outer core was made of again?
Probably not. But yeah, iron.
It's liquid iron. So liquid probably means that it can flow at least a little bit, right? Yeah, so I would say because it's liquid, we probably can assume that there's at least some motion. So we know that this one is liquid iron. So we'll say probably some motion? Question mark? How about the inner core?
No.
No, she says. Why do you say no, probably not?
Probably because it's solid. Not really move much.
Okay, yeah. So, and part of the game is, what does it mean by move, right? Like, we could argue it's part of the earth and the earth is moving around the sun. So it moves, right? Or, I mean, like, you can make that argument. But, like, relative to the earth itself, I'm going to say that the inner core probably doesn't move a lot, right? And the reason for that, Haley, is what?
Solid.
It's solid. So probably little to no motion. Cool. All right. Well done. Yeah.
I said they all move because like the molecules inside of them.
Oh, high five the chemistry thinking there. Yeah, so one way to think about that, right, is that all of those molecules, all of those atoms, the hotter it is, that means the more that it's moving, right? So sure, in that way they all do it. In that way, the molecules in here move a whole heck of a lot, don't they? Because it's really, really hot. It's really hot there, so it's got to move a lot. So yeah, you can say that too. It depends on the kind of motion you're talking about. I love it. Hey, yeah. Good conversation, you guys. I like this. More to add to this. Okay. I'm going to ask a quick question of you to find out where we're at, what you've heard of, what you know about. Have you ever heard of this word? Oops, there's another A in it. Anybody heard? It's pronounced Pangaea.
Oh, I know that one. It's in a movie.
What's Pangaea?
Isn't it like when all the continents on Earth were just one massive continent on Earth instead of broken up as just one? Is that right?
Yeah. So I want you guys to think about. I want you to think about a map of the world. Here's a picture of the map of the world. I want you to look at Africa and South America. And I want you to look at them like a little kid might who's putting a puzzle together. Do you see how the part of Africa that goes in looks very, very similar to the part of South America? And I think is that Brazil? I'm not, my South American geography is not amazing. That sticks out? You see what I'm talking about?
Where are we?
That was
The one at the top. We have an effort.
I'll help you. All right. A little geography lesson. What's it? Oh, you need an extra? Or you have an extra? All right. So I've got a couple more minutes with you. I want you to be quiet. So a little geography lesson for you all. In case it's been a while since you've looked at a world map, okay? This continent right here is Africa, okay? This continent right here is South America, all right? And if you look carefully here, you with me there? It looks kind of like they might fit together. I want you to look at the map. You've got one on that piece of paper in front of you. Question 1, I want you to take a look at it right now. It says, look at the world map to the right. So I've given you one answer, but that's not the only answer. I want you to look at it a little more carefully. Are there continents that you think might fit together like pieces of a puzzle? I want you to see if you can find any other places where things might fit together. You are absolutely welcome to talk to each other. That is fine with me. Take a look at your map. This one or the one in front of you. See if you can figure out any places that might fit together. Bless you.
Bless you. Bless you.
North America.
Turn it around.
Yeah, it's down there. You're right. It's just the picture is not good. You know it's there though, don't you? The colored? Yes, I can. Absolutely. Maybe.
Oh my gosh,
I don't know. I think that there was an update to the software and it messed it up. I agree. I'm not going to disagree with you on that one. It used to just like erase like the whole thing. Like, you know, when you draw a line, it would erase the whole line, which I was used to and liked, and now it doesn't. All right, is that better?
Yeah.
Okay. All right. So take a look answer what you'd actually put your graphite on the paper, make some marks.
Actually, my bad. It's okay. That's my bad.
Write some things down, friends. I want everybody to write some things down on your paper. So you're on the back. There you go. There you go. Do you see any other things that might fit together? What did you guys say? Share some ideas with me. What did you say? Yeah.
So we saw that, of course, South America, Africa,
South America and Africa.
and
So let's be a little more specific here. So we're saying that the east side or the eastern coast of South America and the western coast of Africa kind of fit together, right? This piece here and that piece here, that's what you're talking about? Okay.
and also
What else did you see? Yeah, go ahead, Beth.
Africa and Asia, they're like almost connected.
Like where at? What part of Africa and Asia?
Like the east part of Africa.
Like here
No, like
or up here?
right there.
Right here? So like right where, is that the Red Sea, I think? I don't remember. I think that's right. So you're saying, let's do some color coding. So like this area and this area?
Yeah.
Kind of in the Middle East area? Sure. So you could say the northeast part of Africa kind of looks like it fits with the southeast corner, or excuse me, southwest corner of Asia. Sure. Any other things that look like they might fit together? What was it, Maddie? No? Livy, what you got?
North America is like
North America where?
up at the top. Is that Greenland?
Yep.
Yeah.
So like Greenland up here? And like this part right here? Is that what you're talking about? Or no? Yeah? So Greenland, West Coast, and the northeast of North America? Cool. Tomorrow we get to put the puzzle together. So we'll do some cutting, we'll do some gluing. It's going to be so much fun. You do not have any homework for tonight, though. All right? Have a fantastic day, you guys. I will see you, and tomorrow is Friday. How wonderful is that?